Hello my dear friends, I am Aishwarya Sharma, Civil Wallah, welcoming you once again on the platform Gate Wallah. Guys, today we are going to learn our lecture number 4, which is on flanged beam. Okay, so before this we have covered 3 lectures. One was on properties of concrete, second is the introduction to limited shed method, and the third topic was rectangular beam in flexure. So today we are going to see our flanged beam. It is also simply, you can say, the extension of rectangular beam. Okay, but yes, obviously there are some variations, some differences. So obviously we are going to see all those variations, differences in this lecture. Okay, so once again welcoming you guys. Lecture number 4, flanged beam. Basically the flanged beam are those which are having flanges like I section, T section, L section, but in RCC structures most of the flange section which we are going to use is T section, okay, as well as your L section. Generally L sections are used at the end of the slab, and intermediate beams between the slabs are considered as T section. Okay, I will try to show you in the diagrammatically form. Okay, so these all are the agendas of today's class. So we are going to see how we are going to calculate the effective width of the flange, how we are going to analyze the flange section, and what all are the various possibilities in numerical. So all these 3 things we will be seeing today. My dear friend, flanged beam, basically as I told you, we are going to cover here T section as well as L section, T beam as well as L beam. And the very first step is total this T and L beam, total this flanged beam can be divided into 2 parts. Okay, one is isolated condition and another is monolithically casted condition. Isolated condition is that condition where the entire T beam or L beam is casted at once. After that we are going to put slab over there. But in monolithically casted, my dear friend, the flange of the section is contained within the slab. Okay, so you will not be able to differentiate how much portion of slab is used by the T beam or L beam mechanism. Okay, so we are having some rules there, some IS codal provisions that how we can calculate the exact width of flange. Okay, so there are 2 types of flanged beam, isolated beam as well as slab or you can say beam casted monolithically. After that, my dear friend, if you are looking at the isolated beam, so here the beam is not connected to slab. Here this T beam or L beam and slab are not casted on same time. Means for example, if this is your T beam, so after that only you are going to cast your slab over there. Okay, like that. Are you getting it or not? Okay, so you can see it is isolated beam, so it is in isolated situation, means it is isolated from its surrounding, from its slab, okay, or from some another structure. Okay, so entire this portion is constructed once. After that we are going to cast slab over there. Okay, and next is monolithically casted. Monolithically casted, you can see that this is a continuous arrangement. This is a continuous arrangement, and this is your beam, and you can see this is your slab, and there is some portion of slab which is going to considered in this T beam. Similarly, there is some portion of slab which is going to use in this L beam. Okay, so it is constructed by molding a rectangular beam and slab together. This is important. Okay, and it look like a rectangular beam supporting a slab. If you are watching it from a distance, so what you will see that this is a rectangular beam, and over this rectangular beam there is a slab. It's like that. Okay, but the fact is when they are casted, so they are casted together at the same time. This is the major difference between the isolated beam and monolithically casted beam. So monolithically casted beam, things are casted at the same instances, molding is done at the same instance, and isolated, so beams and slabs, they are casted at different times. Okay, Next is dear very important, how to calculate the effective width of the flange. How to calculate the effective width of the flange. My dear friend, if this is my flange and if you are seeing here the stress distribution, you can see over the entire width of the flange, this stress distribution is not uniform. So in order to make it uniform, sometimes we have to adopt a reduced width of the flange portion in order to make it uniform. Okay, this width has been decided in such a manner that this width into average stress is equal to this width into this constant stress. So by this mechanism, IS code has given some clauses to calculate the effective width of the flange. The task is to make the stress distribution uniform. Okay, but yeah, make sure if by that thumb rule, if you find that this equivalent width is greater than the original width, then equivalent width would be considered as original width, because you cannot produce additional flange width there. Okay, okay dear. Now the next is how to calculate effective flange width in isolated condition as well as in monolithically casted condition. So these are very important. Okay, so my dear friend, if this is your isolated beam, okay, so here if you want to calculate effective width of the flange, let's say BF, so this effective width of the flange is equal to L naught upon L naught by B plus 4 plus BW. But make sure that this calculated BF is always less than equal to the actual BF. Okay, due to the logical reason, because if BF would be greater than original B, in that case you know you will not be able to give additional amount of concrete on the compression side or on the flange side, isn't it? Here the L naught is the distance between the point of contraflexure, or you can say it is the distance between the two consecutive zero moment. B is the original width of the T beam or T beam here, original width. Okay, and BW is the width of the web. So this is BW, it is width of the web. This is DF, it is depth of the flange. Okay, and L naught is in this direction, L naught may be in this direction, and it is the distance between the point of two zero moment. Similarly, my dear friend, similarly for L beam, what would have been here? For L beam, what would have been the case? Here you can see that BF, here you can see that BF is equal to, this BW portion is same here. The difference comes only in this flange. Here the flange portion other than web is half. So what you are going to do, it is L naught upon L naught over B plus 4, make it half or simply multiply it by 0.5 plus BW. Rest of the things are same. Okay, so this is 401, isn't it? Tell me. And yes, here as well the upper limit of BF is equal to B only, means this width only is the upper limit of B. Okay, now after that things, first of all let me ask you if everything is clear. L naught is the distance between two consecutive zero moment, or it is the distance between the point of contraflexure. B is the width. Okay, and BW is the width of the flange, and in no case BF can exceed original width. Okay, next. Now how to calculate the effective width of the flange in monolithically casted case? My dear friend, if it is a monolithically casted case, you can see, and here I am talking about T beam. So how to calculate the effective width of the flange? So here what all are the credentials which would be required? You would be needing L1 and L2. L1 and L2 are the clear span on either side of the web portion of the T section, and you know what is BW. This is BW here, width of the web. Okay, this is the given width, and as I told you, L naught we measure in the transverse direction, transverse to the cross section. So this BF is equal to L naught over 6 plus BW plus 6 times of DF. Or Like there we had the upper limit of BF was B. Similarly, in flange section, in monolithically casted flange section, you do not have any B, any benchmark B, any original width. Okay. So here the benchmark is center to center distance. So whatever is the BF value, whatever is the calculated value of BF, in no case it should exceed center to center distance. So how you are going to calculate center to center distance? If L1 is the clear span on left hand side and L2 is the clear span on right hand side, then center to center distance is mid of this slab to mid of this slab. Okay, so half of L1, half of L2, and with this additional web thickness requirement. So overall BF is L0 by 6 plus BW plus 6DF, or it is the center to center distance, which is L1 by 2 plus BW plus L2 by 2. Similarly, if you are going to apply your common sense, then you can also depict the value of effective width of flange in monolithically casted L beam. So what would happen in monolithically casted L beam? You can see that this BW is going to remain same, and slab is only present on one side and clear span is only L1. So it is going to be BW plus L1 by 2, and other than this BW, these L0 by 6 plus 6DF is going to represent the width of the flanges on another either side other than BW. So we have to simply make them half. So L0 by 6 will become L0 by 12 and 6DF will become 3DF. So if you are applying this logic, so you can see that whenever there is the calculation of effective width of flange in monolithically casted L beam, in that case BF is equal to L0 by 12 plus BW plus 3 times of DF, or BF is equal to how much? It is BW plus L1 by 2. So these are the ways to calculate effective width of the flanges, and all these ways are given in caudal provisions. If you are going to watch IS 456 2000, so you will be going to get these provisions. Okay. I try to make it simplified with the help of diagram and all. Okay. And DF is depth of the flange, and you can also say in case of in case of monolithically casted T or L beam, DF is equal to the thickness of the slab. Okay. So this is the way by which we can calculate effective width of the flanges. Now my dear friend, let me come to the analysis portion. In analysis portion, like we had in rectangular beam, there were total 4 steps: calculation of limiting depth of neutral axis, then calculation of actual depth of neutral axis, after that the comparison between actual and limiting depth of neutral axis, then we used to find moment of resistance. My dear friend, those 4 steps will remain as it is, but that would be one more step would be added here, that is calculation of effective width. Okay, entire analysis is based on effective width of the flange. Okay, first of all you should know that how much portion of your cross section is literally effective, then only you are going to make your analysis as per that, isn't it? So step number 0, so I didn't start it from 1, because 1, 2, 3, 4, now we have a habit of watching. 1 is, yes, it is axial limb, 2 is XU, and 3 is comparison, 4 is resistance. So before those 4 steps, I have added one more step, that is step number 0, calculation of effective width of the flange. So depending upon the type of beam, okay, and nature of its casting, we can obtain the effective width of the flange. Okay. After that, step number 0 is clear to you. Just now we have seen how to calculate effective width of the flange at different conditions. Now step number 1 is what? It is also clear. Calculations of axial limb. So axial limb, as we all know, that it only depends upon the grade of steel. Okay, and Young's modulus remains constant, so it depends upon grade of steel only, and it is independent of geometry of the cross section. So here we can say that axial limb is equal to say 0.53D, 0.48D and 0.46D, depending upon Fe 250, 415 and 500. So in nutshell, I want to say that a limiting depth of neutral axis like there is also a function of grade of steel only. Okay, it has nothing to do with the geometry of the cross section. It has nothing to do with the amount of steel. Okay, it only has to do with the grade of steel, isn't it? After that, step number 2, 3, 4, we are going to club. Step number 2, 3, 4, we are going to club. But before clubbing, let me tell you why this flanged section analysis is slight different than earlier cases. Okay, my dear friend, in rectangular beam, it is easier to calculate XU. How you are going to calculate XU there? You are simply going to equate your tensile forces with the compressive forces. Tensile forces are always equal to 0.87 Fy into AST, but when it comes to compressive forces, it was like 0.36 FCKB into XU. There, the width of the rectangular beam was constant. So 0.36 FCK BXU is always going to work for you. But my dear friend, here can be several possibilities. Here can be the possibility that your depth of neutral axis is going to lie in flange section, in flange zone. If that is the case, then the things would not be that cumbersome. It would be similar, it would be running similar as in case of rectangular beam. Instead of B, you are going to use BF now, and rest of the things would be exactly same. So this is the first possibility of neutral axis. Means whenever the neutral axis is going to lie in the flanged section, so there is no difference in the analysis. Only you have to replace your B with BF, because only this much portion is going to be effective in compression. Only this much portion is going to be effective in tension. So geometry is complicated here, but this complicated geometry is not going to participate in force taking mechanism. Okay, so we don't have to bother about this shape. Okay, so this is possibility number 1 of neutral axis, which is the easiest one, when you can say that your XU is less than, when your actual depth of neutral axis is less than the depth of the flange, when it is less than the depth of the flange. Are you getting it or not? Okay. So this case is quite clear. This case is quite clear. Now what could be the next possibility? Next possibility could be that your XU is greater than DF. Your XU is greater than DF. If XU is greater than DF, here this XU is greater than DF. Okay. But if XU is greater than DF, again there can be some sub cases, you can say. There can be some sub cases. You can check it out here, that this is also the case when XU is greater than DF. You know that this is also the case when XU is greater than DF. But what is the difference between these two? What is the difference between this and that? This is also XU greater than DF. And here as well, you can see that XU is greater than DF. It is not visible, I guess. So let me use white. Okay, are you getting it? So what is the difference between these two? So in this case, XU is quite lower. It is that lower that this rectangular zone portion is greater than that of width of the depth of the flange. Or I can say that this is the case when XU is greater than DF, as well as 3/7 of XU is also greater than DF. What does it mean? It means that is entire flange is going to lie in rectangular stress block. Entire flange is going to lie in rectangular stress block. Are you getting it or not? So what can be the another complexity here? Another complexity may be when XU is again greater than DF, but what is happening here, you can see this is 3/7 of XU, and it is the depth of the flange, this one. So you can see that the 3/7 of XU is lesser than DF. Means here this flange portion is going to fall partially under rectangular zone and partially in parabolic zone. Are you getting it or not? Here this flange is going to share both the stress variations, constant one as well as parabolic variation one. Okay. So here you can say that is flange is lying in rectangular and parabolic stress zone. Okay. So we are going to see that. Okay. So case number 1, when XU is less than DF, no complications. The analysis was exactly like rectangular beam, where we are going to replace B with BF and rest of the things were exactly same. Case number 2, when XU is greater than DF, it is again divided into two sub possibilities. First possibility was when XU is greater than DF, at the same time 3/7 of XU is greater than DF, means entire flange is going to lie in the rectangular stress block. Second possibility is when 3/7 of XU is less than DF, means when the flange is going to lie partially in rectangular zone and partially in parabolic zone. Okay, that was the case. Okay, my dear friend. Now, after that, what is going to happen here? Okay, so if I'm going to you can say club this XU comparison moment of resistance. So you can see there, case number 1, when neutral axis lies within the flange, it is not at all a complicated case. Simply you can see that, yes, step number 2 means calculations of XU is 0.36 FCK, BF XU is equal to 0.87 Fy AST. That's all. Step number 3, comparison. It is comparison. And what about step number 4? Step number 4 says moment of resistance. So you are going to calculate moment of resistance like this. It is 0.36 FCK BF XU into lever arm is D minus 0.42 XU. No difference here, no difference. Exactly same. Isn't it? So things are exactly same here. Second is when your depth of neutral axis is greater than DF. Okay, when your depth of neutral axis is greater than DF, at the same time 3/7 of XU is also greater than depth of the flange, means when entire flange is going to lie under a constant stress block. Okay, so case number 2A, when neutral axis lies within web but 3/7 of XU is greater than DF. So what is going to happen in this case? In this case, what we are going to do, we are simply going to divide this portion into three parts. First is this vertical division, and second and third is the portion in the flange section. So if you are looking at first zone, then the width of first zone is BW, and you can say that this first zone is ditto like your rectangular beam. Okay, so if this is your rectangular beam, then compressive forces is equal to tensile forces, means 0.36 FCK BW into XU. Other than that, there is 2 plus 3. And what is 2 plus 3? 2 plus 3 is the remaining width of the flange, which is falling under the constant stress of 0.45 FCK. So plus 0.45 FCK, okay, into BF minus BW, okay, and into DF. So this is the compressive force due to 2 plus 3. It is the compressive force due to 2 plus 3. This is equal to 0.87 Fy into AST. Okay. isn't it? And again the step number 3 is comparison. Again the step number 3 is comparison. And my dear friend, you can check it out here that there would be two lever arm. First lever arm would be for zone number 1 when this is D minus 0.42 XU, and the second lever arm would be for this portion. Second lever arm would be for this portion, and it is going to lie somewhere here. So if this is dF, then the point of application of this force is the dF by 2. It is dF by 2. I hope you got it, because stress is constant here and depth of the flange is dF. So it would pass through the CG of this rectangular block. So rectangular block CG would be dF by 2. Okay, and for it the lever arm is going to be D minus. It is D minus dF by 2. It is D minus dF by 2. D minus dF by 2. So step number 4 is moment of resistance, and which is going to calculate by 0.36 FCK BW XU into D minus 0.42 XU plus 0.45 FCK into BF okay. So this is a way to calculate moment of resistance when you can say XU is greater than DF and 3/7 of XU is less than DF. Okay. So this is also an easier way. What I did, I simply divide this upper compressive zone into 3 parts, 1, 2, 3. One is completely rectangular, so all you are going to use BW here. And in 2 and 3, what is 2 plus 3? It is BF minus BW. And what is depth? DF. And what is the stress here? Stress here is constant, 0.45 FCK. Okay. So based on that, we have calculated moment of resistance. Okay. Now the next is the third case, when you can see that some portion of flanged portion is going to lie in the stress block, in the rectangular stress block, and some is in the parabolic stress block. Okay. So let's see. Again, I can divide it this flange portion into 3 parts. This is part number 1. This is part number 2, and it is part number 3. So part number 1 is you can say is going to be remain same, 0.36 FCK B into BW into XU, 0.36 FCK BW into XU. This is first compressive force. Okay, 0.36 FCK BW into XU. What would happen to 2 and 3? For 2 and 3, you can see that the portion remaining is this much. This is 2 plus 3. This depth is dF and this width is BF minus BW. So what code did? Here you have observed that there is some portion which is lying in the rectangular zone, and there is some portion which is lying in the parabolic zone, like this. Are you getting it? So this is a complication. Stress is 0.45 FCK. After that, it is gradually reducing. It is parabolically reducing. So this is the real problem here. So what code had suggested? Here code had suggested that decrease this dF such that the stress on the entire 2 plus 3 becomes constant, becomes equals to 0.45 FCK. So code has suggested instead of this, try to make it this. 2 plus 3 is the remaining portion. It is BF minus BW. It is YF. And over this YF, the stress is continuously constant here. Now the stress is continuously constant. Okay, this is the constant stress. This is the constant stress. Getting it or not? And this constant stress is equal to 0.45 FCK. So what we can do here, this is the constant stress. So what we can do here, dear, you can simply see that step number 2 is 0.36 FCK BW XU plus 2 and 3 is C here, BF minus BW into, or you can say 0.45 FCK BF minus BW into YF is equal to 0.87 Fy into AST. Now you might be thinking, what is this YF? So this YF is the reduced depth of the flange, or you can say that equivalent depth of the remaining flange where the stress is uniform equals to 0.45 FCK. Means if you are making DF to YF, you can assume that instead of this rectangular and parabolic variation, the entire stress would be constant and it is equal to 0.45 FCK. Okay, you can see with the YF depth, the entire remaining block is stressed to a constant value of 0.45 FCK, isn't it? And yes, this YF is given by IS code obviously. So this is 0.15 XU plus 0.65. This is the value of YF, 0.15 XU plus 0.65 DF. Okay. So it is clearly visible or not? Okay, 0.15 XU plus 0.65 DF, isn't it? After that, my dear friend, after that, what is going to happen? We will do comparison. Okay, and finally we are going to calculate, where is the next page? Okay, finally we are going to calculate moment of resistance. And how we are going to calculate moment of resistance? My dear friend, just simply see here, nothing has changed here with respect to previous case. The difference only comes in terms of YF instead of DF. Earlier we were taking DF as a reference. Earlier the remaining portion force is 0.45 FCK BF minus BW into DF. Now it is 0.45 FCK BF minus BW into YF. Earlier the point of application of the second and third portion resultant is DF by 2. Now the point of application of remaining 2 plus 3 block force would be located at YF by 2. Earlier the lever arm was D minus DF by 2. Now the lever arm will be, D minus YF by 2, isn't it? So after comparison, what you can do, you can find the value of moment of resistance. So it is 0.36 FCK B W into XU, and lever arm for this is D minus 0.42 of XU, and after that the remaining portion is 0.45 FCK, and it is B F minus BW into Y F multiplied by D minus YF by 2. Okay, this is a way to calculate MU, limiting moment of resistance. I hope it is clear to you guys. Now sometimes there is a confusion among students that how we will come to know which case is suitable, whether it is a case of question number case number 1 or case number 2A or case number 2B. So my dear friend, you have to follow the proper hierarchy. First of all, you are going to make sure that your neutral axis is lying in the flange section. If that assumption fails, means if value of XU is coming out of the range, then you will be going for case number 2, first A, then for B. If automatically case number 2A is also dissatisfied, how it is going to be dissatisfied? XU this time would be greater than DF, but another check 3 by 7 of XU, we have to make sure it is also greater than DF. Okay, isn't it? If 3 by 7 of XU is greater than DF, it means case number 2A is valid. If it is not valid, automatically we will be using this YF case. Okay, so this is the way to calculate moment of resistance. Are you getting it or not? Isn't it? So now we will be switching over to numericals. Let's see the numericals now. Here is first numerical. A T-beam roof section has the following particulars. Thickness of the slab is given as 100 mm. Width of the web, or you can say rib, is 300 mm. Depth of the beam is 500 mm. And center to center distance of beam is 3 meter. Effective span of the beam is 6 meter. And distance between the point of contraflexure, which you can say is L0, is given to you 3.6 meter. Effective width of the flange is going to be how much? So this is a question. Option A 3 meter, option B 1.6 meter, option C 1.9 meter, or option D 1.5 meter. My dear friend, this is a case of monolithically casted T-beam. Okay, so we know how to calculate the effective width of the flange. So what we have studied, that effective width of the flange is either center to center distance, or it is equal to L0 by 6 plus BW plus 6 times of DF. Okay, so center to center distance BF is L1 by 2 plus BW plus L2 by 2. So it is given to you directly how much? It is given to you 3 meter, or you can say 3000 mm. Another is BF is L0 by 6 plus BW plus 6 times of DF. So L0 is the distance between contraflexure, so it is 3600 or 3.6 meter. In mm we are calculating, and width of the web, or you can say width of the rib, is given to you 300 mm and 6 times of DF. What is the DF? DF is depth of the flange, and in monolithically casted section, depth of the slab or thickness of the slab is only the depth of the flange. So it is. So rest of the data you can say is redundant, not required. So 600 plus 300 plus 600. So total it is 1500 mm. So finally you can say the BF would be minimum of these two. So minimum of these two is 1500 mm. So I would like to go with option number D. Okay, I hope you remember my rule. Whenever a question comes in front of you, so you have to pause your video. After that you have to attempt by your own, then you can match your answer with my answer, isn't it? Next question, dear. An isolated T-beam of span 7 meter, which is simply supported, which is going to have the following details, like width of the flange is given to you 1 meter or 1000 mm, depth of the flange is 100 mm, width of the web or rib you can say is 400 mm, and overall depth is given to you, it is 680 mm, effective depth is 600 mm, area of tensile reinforcement, there are 8 bars of 25 mm steel, grades are M20 and Fe415. So you have to calculate the moment of resistance. Okay. So in this question, earlier question was of monolithically casted, and this question is from isolated T-beam. And first of all, we have to proceed with the step number 0, which is the calculation of effective width of the flange. So we know how we can calculate effective width of flange in our isolated T portion. Okay. So let's start. I hope you are attempting it. So first is effective width of flange. First is effective width of flange. Okay, so effective width of flange we have to calculate here. So in isolated condition, BF is calculated as L0 upon L naught by B plus 4. B is original width plus BW. So what is L naught here? L naught here is 7 meter. In mm I am putting. Width is given to you as width of the flange is given to you 1000 plus 4, and width of the web or width of the rib is 400 mm. So if you are going to calculate it, you are going to get 7000 by 11 plus 400. So it is coming out to be how much? So it is coming out to be 1036 point something 36, and it is greater than my dear friends, how much? It is given greater than 1000. 1000 is the given width of the flange. So we will be considering this 1000 mm as our effective width of the flange. Okay. Now another step. Next step is calculation of XU limb. So this is quite easy. XU limb you know how to calculate. It is XU limb is 700 upon 1100 plus 0.87 Fy into D. So directly for Fe 415 it is 48 times of D, and D is how much? D is given to you. कितना दे रखा है D? D is 600 mm. D is 600 mm. So it would be how much? 0.48 times of 600 is 288. It is equal to 288 mm. Third step, I am calculating XU, and I am assuming, first assume XU is in flange only. So if you are using it, then you can write BF XU is equal to 0.87 Fy into AST. Okay. So FCK is 25, and AST is 8 times of pi by 4 into 25 square. FCK is 20 and Fy is 415. So if you are substituting these values, then XU you are going to get, it is equal to XU you are going to get as 196.8, and this XU is greater than DF because DF is 100 mm. So it means this assumption is wrong. So what we need to do now? We have to assume that my XU is greater than DF, and in that case I am also assuming that 3 by 7 of XU or XU limb is also greater than DF. Okay, so that we can use DF formula. If that assumption fails, then we have to proceed with our last option. Is it clear? Okay. So next is assuming XU greater than DF and 3 by 7 of XU is also greater than DF. Means entire flange is lying in rectangular stress block. So which we are going to use, which formula we are going to use? It is 0.36 FCK, it is portion number 1, BW, XU plus the remaining portion which is constantly stressed. This is equal to 0.87 Fy into AST. BW is 400 mm, FCK is 20, and BF is 1000, BW is again 400, DF is 100, Fy is 415, and AST is 8 times of pi by 4 into 25 square. So on solving this equation, you are getting the value of XU, and this XU is coming out to be how much? 304.5. 304.5. And my dear friend, this 304.5 is greater than XU lim. So we are going to take our benchmark as XU lim. So adopt XU equals to XU lim. So what is 3 by 7 of XU lim? 3 by 7 of XU lim is 3 by 7 of XU lim was step number 1, it is 288. 288. So on solving this, you are going to get how much? On solving this, you are going to get it is 123. It is 123, and luckily, fortunately, this is greater than DF, which is 100 mm. Okay, if this would have been lesser than 120 100 mm, in that case we have to proceed with the case number 2b, means YF case. Okay, now the things are quite clear that our case is lying in case number 2a. Okay, so we will be using we will be calculating its moment of resistance as per DF formula. So what is the moment of resistance now? So final step, calculation of moment of resistance. So mu is 0.36 FCK BW XU into D minus 0.42 of XU plus remaining portion is 0.45 FCK BF minus BW DF, and its lever arm is D minus DF by 2. So substituting FCK as 20, BW as 400, XU as XU lim, XU ko, my dear friend, XU you are going to place at as XU lim. Here as well, place it XU lim. Okay, so you will be getting the value of mu. So mu is also limited to mu lim. So mu lim is coming out to be how much? It is coming out to be 694.3. 694.3 in kilonewton meter. I am writing. Okay, so this is the final moment of resistance, or you can say the limiting moment of resistance of this case. Is it clear? Are you getting it or not? So my dear friend, these are two numericals which explain you the calculation of BF in isolated beam as well as in monolithically casted beam. So it doesn't matter whether your T-beam flange section is monolithically casted or isolated. So it is going to adopt the same procedure. The only difference lies in the calculation of BF. Okay, so BF calculation we have seen in both of these cases. Is it clear? Okay, so that's all in this lecture, and we will be meeting again I think day after tomorrow, and on that day the topic would be shear. Okay, thank you guys, thanks a lot.